Many people today can predict how the sun and the earth will eventually come to an end. But what about the entire solar system? How will the whole system collapse, and how will it completely disappear? In today's video, I'm going to explain all of this to you in great detail. If you enjoy this type of content, don't forget to subscribe to my channel, like the video, and leave a comment to share your thoughts. Now, if you're ready, let's begin. One of the most fundamental laws of the universe, the second law of thermodynamics, reminds us of a very simple yet terrifying truth. In closed systems, disorder, also known as entropy, always increases over time. This rule does not only apply to laboratory experiments, but also to all cosmic structures, from stars to galaxies. In this context, the solar system is not a static structure. Rather, it is a dynamic system sustained by energy flows, evolving over time, and ultimately destined to collapse. Formed approximately 4.6 billion years ago from the collapse of a massive molecular gas cloud, our Sun is currently a G-type main sequence star. It produces almost all of its energy through proton-proton chain reactions occurring in its core. In this process, 4 hydrogen nuclei fuse together to form a helium nucleus, and a small portion of mass is converted into energy. This transformation is explained by the famous equation E equals mc squared, which even people with no background in physics have likely heard of at some point. The temperature in the sun's core reaches extraordinary levels, around 15 million Kelvin. Under these extreme conditions, the electrostatic repulsion between hydrogen nuclei can be overcome thanks to quantum tunneling. This is a process that classical physics would not allow, but quantum mechanics makes possible. The Estomaro fusion reactions depends on the hydrostatic equilibrium established between the sun's internal pressure and gravity. This balance is mathematically described by 4 fundamental differential equations that define stellar structure, mass conservation, hydrostatic equilibrium, energy transport, and energy generation. When these equations are solved together, the life cycle of a star can be predicted with very high accuracy, even if not with absolute certainty. However, there is a very critical detail here. The sun does not use its fuel uniformly. Fusion occurs only in the core, which leads to the accumulation of helium over time. While hydrogen decreases, helium cannot undergo fusion at the current temperatures and behaves almost like ash, accumulating at the center of the core. This buildup is the most critical factor that determines the future evolution of the sun. As time passes, the amount of hydrogen in the core decreases. Contrary to what many people might think, this does not slow down energy production, it actually increases it. While this may seem counterintuitive, the logic is quite simple. As hydrogen decreases, the core begins to contract, and this contraction increases the temperature. The rise in temperature accelerates the rate of fusion. As a result, the sun becomes brighter over time. However, this process is not linear. The sun's luminosity increases by approximately 10% every billion years. Although this may seem like a small increase, even this change can lead to catastrophic consequences on a planetary scale. This is especially critical for our planet, Earth. The Earth's energy balance, as I mentioned in a previous video, is based on the equilibrium between incoming solar radiation and the infrared radiation emitted back into space. As the sun's luminosity increases, this balance is disrupted. Surface temperatures rise, accelerating evaporation. As a result, much more water vapor enters the atmosphere from the oceans, and water vapor is a very powerful greenhouse gas. Let me briefly explain how greenhouse gases work. As temperatures rise due to the disrupted balance, greenhouse gases trap heat within the planet. This causes temperatures to increase even more rapidly and uncontrollably. This runaway process is known as the runaway greenhouse effect. In fact, there is a perfect example of this phenomenon within our solar system, Venus. Climate models for Earth show that within approximately 1 billion years, the oceans will largely evaporate. At this point, water molecules in the upper atmosphere are broken apart by ultraviolet radiation from the sun. Hydrogen escapes into space, while oxygen reacts with surface rocks. This marks the beginning of an irreversible process. The Earth gradually transforms into a planet with no water, no oxygen, and extreme temperatures. Photosynthesis stops, the carbon cycle collapses, and all complex life as we know it disappears. During this phase, only microorganisms capable of surviving extreme conditions may remain, but even they will not last long. As the sun continues to evolve, there is no stopping this process. Eventually, the atmosphere becomes extremely thin and reaches the brink of disappearing entirely. The Earth turns into a planet resembling present-day Mars, perhaps even more dry and lifeless. At this point, one crucial thing must be understood. The end of the Earth is not a sudden catastrophe or an instant apocalypse, but rather a gradual collapse spanning billions of years. And the real breaking point actually begins after this. Because once the sun completely exhausts its hydrogen, the system enters a far more chaotic phase. This is the stage where the sun begins its transformation into a red giant. After the hydrogen in the core is depleted, the core can no longer sustain stable fusion. At this point, the sun leaves the main sequence phase and transitions into the stage known in stellar evolution as the subgiant phase. During this process, even though hydrogen in the core is exhausted, energy production does not completely stop. Instead, fusion continues in a very thin shell surrounding the core. This process is called hydrogen shell burning, and it plays a decisive role in the star's evolution. At this stage, a critical physical mechanism comes into play. Since there is no longer energy production in the core, gravity becomes dominant and the core begins to contract. This contraction is known as gravitational contraction, and it causes the core temperature to increase dramatically in a highly unstable manner. As the temperature rises, hydrogen fusion in the surrounding shell accelerates even further. This means more energy is transferred to the outer layers of the star. As a result, the outer layers of the sun begin to expand. At a certain point, this expansion becomes so extreme that the radius of the star increases to hundreds of times its current size. At this stage, our sun is transformed into a red giant. During the red giant phase, the surface temperature decreases, but the total luminosity increases significantly. This is because the surface area of the star has expanded enormously. According to the Stefan Boltzmann law, the total energy emitted is directly proportional to the surface area. This expansion is essentially a death sentence, especially for the inner planets. First, Mercury is engulfed by the expanding atmosphere and completely destroyed. Then Venus is entirely vaporized and mixed into the outer layers of the sun. The fate of Earth, however, depends on very delicate balances. As the sun loses mass, its gravitational pull weakens, which could cause Earth's orbit to expand outward. However, tidal forces and interactions with the sun's extended atmosphere can also pull Earth inward. In other words, Earth is essentially being tugged back and forth between these competing effects. During this process, two main mechanisms are constantly competing with each other. The first is orbital expansion due to mass loss, and the second is orbital decay caused by tidal friction and atmospheric drag. Most advanced models today suggest that the second effect will dominate, meaning that Earth will ultimately be engulfed by the sun. While all of this is happening, the most dramatic event of the red giant phase has not yet occurred. That event is the onset of helium fusion. As the sun's core continues to contract, the temperature rises to around 100 million Kelvin. At this temperature, helium nuclei can fuse to form carbon. This process is known as the triple alpha process. Under normal conditions, this reaction begins in a controlled manner. However, in low-mass stars like the sun, the core exists in a very different physical state, a state known as degenerate matter. Electron degeneracy pressure is fundamentally different from classical gas pressure. This pressure does not depend on temperature, but on quantum mechanics. This means that when the core heats up, it does not expand and cool down as expected. As a result, the star's natural self-regulating mechanism is effectively disabled. The outcome is a runaway fusion explosion. This event is known as the helium flash. The helium flash releases an enormous amount of energy in just seconds within the sun's core. This energy can reach billions of times the sun's current total energy output. However, interestingly, this massive energy release and explosion cannot be observed from the outside. This is because the energy is used to break the degenerate structure of the core. The core suddenly expands, its density drops, and the system returns to equilibrium. This event completely transforms the internal structure of the star. At this point, the sun effectively becomes a new type of star, now burning helium in its core. This new phase resembles a stable state similar to the horizontal branch. However, this stability does not last long. Once the helium in the core is also depleted, the process repeats itself. This time, carbon and oxygen begin to accumulate in the core. However, the sun does not have enough mass to fuse these heavier elements. This means that the sun will enter the final stages of its life cycle without producing heavier elements. During this process, the sun becomes increasingly unstable. While intense convection currents form in its outer layers, the star periodically expands and contracts. These oscillations cause material to be ejected from the star, and the sun essentially begins to throw its own mass into space. At this stage, the star enters a phase known as the asymptotic giant branch. In this phase, fusion occurs in two separate shells. In the inner shell, helium burning takes place, while in the outer shell, hydrogen burning continues. This double shell structure is extremely unstable and leads to explosive events known as thermal pulses. Each pulse causes large amounts of gas to be stripped away from the star and dispersed into space. This ejected material will later form the raw material of a planetary nebula. As the sun gradually approaches the end of its life, it begins to lose its outer layers completely, leaving behind only its exposed core. This process marks not only the death of a star, but also the beginning of the complete disintegration of a planetary system. After the sun completes its red giant phase and ejects its outer layers into space, only a dense and hot core remains. This remnant is known as a white dwarf. In this new state, nothing remains of the sun as we know it. It has lost a significant portion of its mass and no longer produces energy through fusion, yet it remains a compact object with a strong gravitational field. And it is precisely at this point that the most critical change determining the fate of the solar system occurs: mass loss. During the red giant and asymptotic giant branch (AGB) phases, the sun loses approximately 50% of its total mass into space. This means that the gravitational potential of the system decreases dramatically. According to Newtonian mechanics, a planet's orbit is directly dependent on the mass at the center. When the central mass decreases, planetary orbits expand. We can think of this process in a simple way. If you loosen the string of a stone spinning on it, the stone begins to trace a wider circle. The same principle applies to planets. In this new configuration, Jupiter plays a key role as it is the most massive planet in the system. As the sun's gravitational influence weakens, Jupiter's relative influence increases. The dynamic architecture of the system is now shaped more by the giant planets than by the star itself. This transforms the solar system into a chaotic multi-body system. The n-body problem tells us that the gravitational interactions of three or more bodies cannot be solved analytically. This means that even though the system is deterministic, its future becomes practically unpredictable. In this chaotic regime, even small deviations can lead to massive consequences. Orbital changes that may seem insignificant over millions of years accumulate over time, eventually leading to close encounters between planets. These encounters result in the transfer of energy and angular momentum. From this point on, three main scenarios emerge. The first scenario involves the ejection of planets from the system. During close encounters, a planet can gain kinetic energy from another. If this energy exceeds the escape velocity, the planet can no longer remain in a bound orbit. In that case, the planet completely escapes the system and becomes a rogue planet. I've actually talked about these types of planets before. If you're curious, don't forget to check out that video on the channel. Anyway, outer planets like Neptune are much more susceptible to this outcome because they are farther from the central mass and their orbits are more fragile. As a result of this process, the solar system may lose its planets one by one. Our second scenario is based on collisions between planets. In this scenario, chaotic orbits do not only lead to escape, but also to catastrophic impacts. When the orbits of two planets intersect, collisions at extremely high velocities release enormous amounts of energy. Such impacts can completely shatter planets, or in some cases merge them into a new, larger mass. This process is essentially a late-stage version of the giant impacts that shaped the early solar system. Resonance instabilities, especially between giant planets like Saturn and Jupiter, can destabilize the entire system. The final scenario involves planets falling into the white dwarf. Some planets may lose energy and gradually shrink their orbits. This typically occurs due to tidal interactions and friction with surrounding debris disks. In this process, planets slowly spiral toward the remnant of the sun. However, this is not a sudden collision. It is a gradual process that unfolds over long periods of time. As a planet approaches the white dwarf, it is subjected to immense tidal forces. These forces can tear the planet apart, forming an accretion disk. Over time, this disk falls onto the white dwarf, causing short bursts of brightness. In fact, the presence of heavy elements in the atmospheres of some white dwarfs we observe today is strong evidence of these planetary consumption events. Although these three scenarios are described separately, they can actually occur simultaneously or even on different timescales. In other words, while some planets may become rogue planets, others may fall into the white dwarf, and the remaining ones may collide with each other, leading to all three outcomes at once. Beyond this point, the fate of the solar system is no longer determined solely by its internal dynamics. Instead, it becomes dependent on a much larger structure, the Milky Way galaxy. Within the Milky Way, stars are not stationary. Each one moves around the galactic center and, over time, they can approach one another. Although these motions may seem insignificant on timescales of millions of years, over billions of years they inevitably lead to encounters. Most of these are distant flybys, but some can be close enough to have dramatic consequences. Even a passing star at a distance of a few hundred astronomical units could have devastating effects on the solar system. Such an encounter could severely disrupt planetary orbits, eject objects from the system, and completely destabilize the remaining structure. For a system that is already weakened and partially disintegrated, these effects can be fatal. But the truly monumental event will occur in about 4 to 5 billion years, the collision between the Milky Way and the Andromeda galaxy. Contrary to popular belief, this event will not completely destroy the galaxies. In fact, because the distances between stars are so vast, direct stellar collisions will be extremely rare. However, the real source of chaos will be gravitational interactions. During this interaction, stellar orbits will be altered, new star formation may be triggered, and existing systems will be scattered. The solar system may either be relocated to a different region of the galaxy or ejected entirely into intergalactic space. Already in a state of collapse, the system could end up drifting through the dark void of the universe in a completely shattered form. Trillions of years after the sun becomes a white dwarf, it will cool down completely and turn into a black dwarf, a dark, cold remnant that emits no light and produces no heat, silently drifting through space. If anything still remains around it, those remnants will be frozen, lifeless, and engulfed in darkness. And that's it, my friends. The end of the solar system is not determined solely by its internal dynamics, but a very large part of it will unfold after the sun becomes a red giant and gradually fades away. Based on my own research, all three scenarios I described will likely occur. Some objects will fall into the white dwarf, some will be ejected from the system, and others will collide with each other. But don't worry, such an end is still billions of years away. Hopefully, as humanity, we will survive long enough without destroying ourselves and develop advanced technologies that allow us to carry our ecosystem to other worlds. Who knows, maybe one day future humans will sit back with their drinks, watching the ruins of the solar system, imagining these very days described in ancient records, and perhaps even thinking about us. Thank you for watching the video. If you want to support me and enjoy this type of content, don't forget to hit the like button. It's incredibly important for the algorithm. Subscribe to the channel and leave a comment to share your thoughts. See you in the next video. Until then, take good care of yourselves. Goodbye.